Saxon Advanced Mathematics, Lesson 8. Greetings, my students. We are, I didn't write this, Lesson 8. We are going to start inching our way toward doing proofs. Shake off any past history that you've had with proofs that isn't positive. We're going to take it easy and we're going to make it fun. And we're going to see the logic of doing this. Not logic like the last lesson, but we're going to see the kind of natural ideas flow. And we're not going to worry a whole lot about the details. We'll build that as we come. The idea of proofs is usually, at least the ones that we're going to do, is we're trying to prove I left out a letter. Congruency. Oh, that's sad. I ruined it. Congruency, which means equal in geometry. We don't say that two triangles are equal. We say that they're congruent, which means they have the same angles, same size angles, and the same sides. By comparison, we sometimes do proofs to prove similarity. And with those, the shapes aren't exactly the same. They have the same angles, but they have different length sides. Okay, so this is what most proofs are doing, is they're giving us a shape or a couple shapes, and they're asking us to either prove congruency or prove similarity. All right, we're going to baby step into this. And we've got a triangle that looks like this. I think we've started to look at these. Think of it as triangle stickers, right? We have to peel them apart. What John is asking us to do is to show, let's see, it says in triangle ABC, segment BD is the altitude to the hypotenuse AC. Okay, so it's saying this meets it at a right angle. That's what altitude means, is it meets it at a right angle. Okay, show the following. AD, okay, John's giving us all this. All right, so he wants us to build proportions. Let's see exactly what he's looking at. A to D is this, A to B is that. So he's looking at the base, the short leg, and the hypotenuse, if you see it as this little triangle. And he's asking us to compare that to AB to AC. That's, if now we have to switch and look at this as the big triangle, I'm going to draw this in just a second. If we look at this as the big triangle, that's the short leg to the hypotenuse of the big triangle. So this looks like it's short leg over hypotenuse. And what we're going to do is we're going to just quickly sketch out these three triangles to see if that looks like what we're doing. Okay, so this is going to be the little triangle, A, D, and B. We know that this is a right angle right there. Now we're going to draw the medium-sized. The medium-sized is this one. It's got C at the top, it's got D in the corner, and it's got B over here. Right? C, D, B, C, D, B. The order that we state angles in matters and triangles. We always want to put them in the same order. So if I was, oh wait, I did something wrong here. This is D. This would be triangle ADB. This would be triangle BDC. We want to keep the letters flowing in the right order. All right, and then we make our big triangle. And we have to orient ourselves to see that. At the corner, we have angle B. C is up at the top, and A is at the short end. Yes. I'm just going to rewrite that closer to the corner because I was confusing myself with that. All right. So we're trying to prove, I'm going to use some different colors. We're trying to prove that AB I did the wrong one. I'll do it over here. This is AB is the same as AC. They're proportional. And AD is proportional to AB. Okay, so that's the orange and the red. Okay, so that all of that work all of this work was just to understand what the problem is. Okay, so here's the thing. So we have to prove somehow, we aren't really concerned with that middle triangle. We have to prove that these are similar. If these two triangles are similar, a cool thing about similar triangles is that they have proportional sides. So if we can prove that these triangles are similar, which again means they have the same angles, then we prove that they have proportional sides, and then that we'll be proving that this is true. Okay? Can we prove that triangle ADB is similar to triangle ABC, right? ADB, ABC. Those are the two. We want to prove that they are similar. And that's what that kooky little thing means. Yes, we can prove that because they share an angle A and they share a right angle, right? They both have angle A and they both have B, so that means that this angle up at the top, let's give that one 2. Just trying to make it clear what I'm showing you. We know that these two triangles are similar because they both have an angle A here, they both have a right angle, and if we have 2 angles, then the third one must also match. We're going to talk about that later. So we know for sure that this is true. We proved that they are similar. Okay? If we prove that they're similar triangles, then we know that their sides are proportional, and we can say that this is kind of the main area of my proof here. All the rest is laying out the ideas. So our first step was to say these two triangles are similar because they both have an angle A and they both have a right angle. So that means that if 2 angles match, then the third must also match. The next thing we want to say is that if two triangles are similar, then their sides are proportional. So that means that AB is proportional to AC, and it means, I don't want an equal sign there, and it means that AD is proportional to AB, and it means that, we'll start at the top, BD is proportional to CB. Okay, so I wrote those segments. This is the middle. The pink ones are the first ones, right? AB to AC, that's what I have here. The middle one is the bottom ones, AD to AB, that's what I have there. Smaller triangles always on the top, larger triangles always on the bottom. And then the third set of pairs is BD to CB. That's the third set of pairs. Now, what John wants us to prove is simply this, only rearranged. He wants us to say that the ratio of these two oh no, I've got it, don't I? Yeah, this is the same as this, and this is the same as this. So once I prove that these two triangles are similar, I can write out the pairs of proportional segments, and I have proved what I wanted to prove. This is what we set out to prove, is that this is true. And there they are right there. Okay, so what we are trying to do is we're trying to learn how to take shapes, separate them, we often have to do as a first step, and then find out the similarity of them and then draw conclusions about the specific parts. We'll do more, it'll be fine. Let's look at another one. Proportional segments. Here's our shape. Notice that these two lines are parallel. We're told that those angles are the same. We're told that these angles are the same. This is angle M. That's the only one that's labeled. Then we get lengths of sides. So this time we're not talking about the angles. Well, we are going to talk about the angles. It's all important. Okay, so this isn't the one I wanted to draw. Well, we'll just go ahead and use it. We can separate this into two triangles, right? We can peel them apart. This visual process is really at the heart of how to do these problems. I'm peeling off that top triangle and I'm going to put it here. And this is M, this is A plus B, and this is C plus D, and this is Y, but we're told those are the same. Now, do we know if these angles are, if these two triangles are similar? How would we tell? We need to prove that they have the same angles. Well, we know that this angle is the same, and we know that that one's the same, right? They share that one in common, they share that one common. If we have two, then the third one must also be the same because they have to add up to 180, right? So if you have two, the third one has to match. So we can say, yes, they're similar, okay? Once we say that they're similar, we know that their sides are proportional. We talked about that last time. This time, we can say that A plus B over A, this side, big triangle over little, is going to be proportional to C plus D over C, big to little, okay? And we could also say, oh, this is X. I didn't put that on the original picture. And so this side is X. We can also say that Y, because we're doing the big triangle on top, is proportional to X. All right, so these things are all true, and we're going to use this. This is the actual example, 8.2. Find X. Oh, okay, so this is getting algebraic on us. We're not going to talk about proofs. We're going to use this in a very practical way, which I kind of like better. Okay? We know that these guys are proportional. x plus 1 over 13 is going to be equal to x plus 4 over 19. The reason we know that they're proportional is that when transversal lines cut the same set of parallel lines, their proportions, these segments, are proportional. You knew that. I know you knew that. So that's why we can write, okay, top to bottom equals top to bottom. The proportion will be the same. The absolute lengths aren't the same, but the proportions are. These are all parallel lines, so that's important. Okay, so now we can solve this by cross multiplying. 19 times x plus 1 quantity equals 13 times x plus 4 quantity. Distribute. Let's swim the 13x this way and the 19 that way. It'll keep our numbers positive. All right? Give you a second to catch up. I can reduce that, taking 3 out of each one. Okay, so we used what we know about geometry and proportional segments to set up an algebra problem and solve for an algebraic value. This is not the length of any one of these segments, but it's an algebraic answer. We could use it and plug it back in if we wanted to get those absolute lengths, but we don't need to. Okay, flipping. The last category we're going to talk about, and again, we're going to take geometry and use it to solve some algebra problems, and this is about angle bisectors and side ratios. And I'll show you the truth of it first, and then we'll apply it. Okay, when we have a line that perfectly bisects an angle, I'm trying to make those two angles equal, and it comes down, it will also create proportional sides here. Okay, so let me show you what I mean by that, because the words are not helping. Okay, I'm circling these so that it's really clear. I mean the sides. Because these two angles are the same, we can say that A is to B as C is to D, right? So we can set those two proportional to those two, or we can say A is to C as B is to D. Both of these are true. And we can use them however we want to solve algebra problems, okay? So this is a bisector that cuts those into equal angles, and then it creates these nice proportional relationships between the existing sides and then the two bits of the opposite sides that have been bisected. So that's angle bisectors and side ratios. Okay, there's a proof at the top of page 64 that shows you why this is true. If you wake up in the middle of the night haunted by the idea that I've told you that this is true but you don't know why, you can go back to page 64 and look at the optional proof. Otherwise, I'm going to pass over that and assume that you would prefer more practical knowledge. Example 8.3. Now we're going to use this with some algebra, which, like I said, it's much more satisfying to me. Okay, these two angles are equal. That's what the tick mark shows us. Angle B has been bisected, and that makes us happy because we know now we have this great set of relationships. 10, 15, x, and 12. Those are the lengths of the sides and the two bisected bits. All the angles have letters on them, although I don't think we're going to need them. This is actually C, and this is D. Okay, we want to use this information to figure this out. It says, in triangle ABC, segment BD is the angle bisector of angle A. Okay, so that's saying that this is the angle bisector of angle B. Okay, we knew that because of these little marks, right? It already shows that we chopped that into equal parts, but he's telling us this divides that perfectly evenly. So now we know our proportions will hold out, and we are being asked to solve for x. Okay, so we can set our proportions up in either of these formats. I find it most logical to go like that. So I want to go 10 over x equals 15 over 12. If you do it the other way, it will still work. Let's just set it up the other way. Let's see, I went like this, so it would be 10 over 15 equals x over 12. Those are the two ways, right, that you could set it up. Let's cross multiply. 10 times 12 equals 15x, and look what happens here. 10 times 12 equals 15x. So, whichever way you set it up there, once you cross multiply, you have the same problem. And we're going to divide by 15. In these problems, I do not multiply this out yet because I want to keep my numbers small. I know I'm going to have, whenever I cross multiply, I just leave it like that because I know that John will probably give me some numbers that reduce. I'm going to take 5 out of both of those and get 2 and 3. And then I'm going to take 3 from 12 and get 4. So what I get is that x equals 8, and that's the correct answer. One more, and we are done. This triangle has flopped over. John's trying to confuse us by giving us this weird looking triangle, but it's not going to throw us off our game. This is bisected. Pretend that's perfect. This is x. This is 20. This is 14. And this is 6. Let's see what the problem says. In triangle ABC, segment AD is the angle bisector of angle A. Okay, that's a good news. It tells us all that is true. Find x. All right, the only thing we have to do is just kind of mentally take this and turn it so that we can see the pairs more clearly. I can see, my tendency again is to do 20 over 14 equals x over 6. And we could do it the other way. I didn't leave myself enough room, which would be 20 over x equals 14 over 6. Right? This is the alternate version. Just as this was the alternate version. Puffy cloud of knowledge. That's a puffy cloud of knowledge. I don't know if I've explained that. But whenever I put something in a puffy cloud of knowledge, you would be wise to write it down in your notes, back of the cover. It's important. That's what I'm saying. All right, so now we cross multiply. 20 times 6 equals 14x. Whoops. X. And I'm just going to double check my alternate one to make sure. Yeah, 20 times 6, 14x. I would get the same thing, so that's satisfying. Divide both sides by 14. I'll do 7 and 10. And our final answer is 60 over 7. That would be the side of that length. What do you think? We're easing our way toward proofs. We're playing with geometry. We're spinning in some algebra. And we're, like I said, we're slowly moving our way toward next lesson, lesson 9, which is called proof outlines. So we're going to start organizing our ideas a little bit more. But again, it's not a full proof yet. It's just helping you to understand the thought process. You don't have to worry about that for now. Okay, the last thing I want to remind you is office hours. I've changed them a bit. Some people just can't meet on Friday, so I'm adding a Thursday session. If you can meet me on Friday, that's my ideal, you guys. I think that's a much better time to meet because we're at it's psychologically better because we're at the end of the week. You might still have some homework to do over the weekend. That's fine. That doesn't bother me. But if you can connect with me on Friday, that's my ideal. Thursday I'm just doing because a lot of people have busy Friday classes. So do what works best for you. Lean in on the Fridays if you can. I look forward to chatting with you. If you have any questions, holler. That's all I have to say. Enjoy your day. Thanks, you guys.